Next is our main focus is in approach number 2, which is drawing the same voltage across each power source while these power sources are serially connected to supply the load. In this approach, the excess amount of power is parallel processed by the DC-DC converter that programmed to have the uniform voltage sinks across each power source. And this parallel processing of power can be considered as the excess energy or power to charge into energy storage such as battery backup. In this particular control, only one MPT controller is used to control the sourcing voltage of all serially connected power source to be equal voltage, and control uniform voltage distribution across individual power source. This slide shows the power versus voltage characteristics of this particular approach that become the main focus of this presentation, which is called uniform voltage distribution. This particular approach delivers the peak power of 831 watts, which is slightly below the ideal peak power achieved by the base approach 842 watts that achieved from the independent maximum power tracking. The approach number 2, using single maximum power tracking controller with uniform voltage distribution, provide the tracking efficiency of 98.7%, which is considered sufficient and acceptable for most applications. This slide shows the power versus voltage PV characteristic of each power source that involved in power transfer to the load and excess power transfer to the power converter that may use to charge the battery through the control of uniform voltage distribution across these power sources. All power sources always become power provider. None of them become power dissipator. This is the beauty of uniform voltage distribution that allow these powers stay in the active and able to provide or sourcing power into the system. As a result, the weak power source able to provide peak power of 90 watts. The second power source in blue able to provide peak power of 352 watts, and the strongest power source, which is in yellow, provide the peak power of 400 watts. When these three power sources combine using uniform voltage distribution, the next peak power happen at the load total sourcing voltage of around 104 volts happen at 832 watts. This slide basically emphasizes the feasibility of energy harvesting based on uniform voltage distribution among serially connected power sources. Uniform voltage distribution control provides a nearly ideal transfer of the optimum power with less control complexity while preserving power fault tolerance. Utilizing Siri connected power source and series input parallel output converters or SIPO converter. These SIPO converters are controlled to achieve their uniform input voltages across their respective power sources, while also tracking the system optimum power point being sufficiently close to the ideal system peak power. Optimum power transfer of uniform voltage distribution. The system optimum power by definition is the maximum power drawn from the series connected power sources while their voltages are kept uniformly distributed or equal. With proper uniform input voltage distribution control and optimized utilization of the power sources is achieved by employing only one MPT controller instead of multiple maximum power tracking controllers employed in the conventional approach, which each controller being dedicated for its respective power source. This slide summarizes the power versus voltage characteristic of three approaches mentioned previously. The approach of independent maximum power tracking shown in red curve review 842 watt peak power. The optimized approach, which is the approach that becomes the focus of this presentation, is uniform voltage distribution group tracking control approach, deliver 831 watts. The worst approach only deliver around 742 watts. The group track maximum power tracking control with uniform voltage distribution has achieved over 98% tracking efficiency in most manageable circumstances, as shown in blue trace labeled as GT UIVD.